Alrighty, I think we're good to start then. So welcome, hello to whoever's grading this. This is my circuits final. So the task that I wanted to do is I wanted to create a circuit that would charge a capacitor, then have that capacitor power an LED for a short time. And then if a secondary switch is hit, it would keep the LED on forever. This is the circuit I created. So if we look at the bottom left, we've got a battery that would power the capacitor, and then a switch that would allow the capacitor to power the LED. And then on the bottom right, we have a battery that is connected directly to the LED. And so if this switch is hit, the switch on the very right, it would power the LED permanently. We also have a potentiometer in series with the LED that would allow the brightness to be changed. And both batteries are 7.2 volts, which would just be 1.8 volts in series. So first, this is what I did when I labeled it. I labeled nodes A and B, and I labeled the left switch in position 1 and position 2, and then the right switch would just, I labeled switch 3. We're going to look at it when it's closed later. So when the left switch is down in the first position, we can use KVL to analyze the loop, and we get a voltage drop across the capacitor, and that's the equation we get. And for my research, I found that the maximum voltage of a Panasonic 10 microfarad capacitor is 100 volts. Now, if we take the limit as t approaches infinity of the voltage drop across the capacitor, we get 7.2 volts is the maximum. And so that's much less than 100 volts. And so that's all good. We're still within the boundaries. Now, if we do KCL at node B, we know that the current through the whole loop must be equal. And so we get the exact same equation. So that verifies the first result, that it stays within the boundaries and that the math is correct. Next, we're going to look at if the left switch is in the top position, in the second position, and this is when the capacitor is going to be charging the LED. So first we have KCL at node A. This is where the currents are going to be equal. And so from there we get an equation for the current through the whole loop, I2. And we know that through my research, I found that the maximum current for Panasonic resistors, whether it's the 750 ohm or the 500 ohm, is 1 amp. And so if I look for the current at 0 seconds, we find that the max current is 14.4 milliamps, or 0.0144 amps, which is much less than 1 amp, so it's still within the bounds. Now, if we use KVL, I get the exact same equation, which verifies the math and the numbers. All right, now we're going to look at what happens if the secondary switch is flipped. So this is going to be when switch 3 is closed, and then when the left switch is in the first position. First, we're going to do KCL at node A. The current through the whole loop must be equal. And so we get a relationship between the voltage at node A and the voltage drop across the LED. Now, through my research, I found that the optimal voltage and max current across a X lamp white LED is 2.9 volts and 1 amp. So we plug a 2.9 volts in, we can solve for V sub A, which would be 5.48 volts. Now, if we solve for the current through that loop, we get 0.00344 amps, which is much less than 1 amp. So that's still within the bounds. Now, if we do KVL, we get a similar equation, not exactly the same, but it relates the voltage across the LED to the current through the whole loop. And so if we plug 2.9 volts in, we get the current through the whole loop is 0.00344 amps, which is the same answer as we got before, and still less than 1 amp. So this verifies the result. Now we're going to go take a look at the simulation I made on Falstead, which is this, right? So in the bottom left, we've got the capacitor charging. We've got the LED. We've got the switch that will allow the LED to be permanently powered. And then I've also set up a voltmeter and an ammeter for both the capacitor and the LED. So now if I start this, you'll see that the capacitor is being charged very slowly. And I'm going to speed this up. And so eventually it's going to get up to 7.2 volts. There we go. So it's about 7.2. Once at 7.2, let's slow this down a little bit. I'm going to hit switch. And the LED is going to be charged or powered, excuse me. So now it's going to be powered. And if I change the resistance, it changes the brightness. So it's much darker there. And it's much brighter there. So over time, this LED is going to get dimmer and dimmer and eventually go out. So if you speed this up. So there it is. It just went out. So now we're going to close this one. And we're going to close the right one. So let's bring this resistance down. And when I open that, when I when I close that switch, you'll see that the LED is permanently powered. So this is never going to go out as the LED is connected directly to the battery. And if I change the resistance, the brightness changes slightly, not as drastically as the capacitor. But yeah, I mean, this does what I asked it to. I asked for a capacitor to be charged. I asked for that capacitor to then charge power an LED. And then I asked for the LED to be powered by some other source. And that's what this does. Thank you guys very much for everything this semester. Hope you guys have a great summer. And yeah.